This example is going to hopefully help you understand our last set of transformations. Okay, so in the previous set, we had a multiple outside of the operation, right? We had a multiple outside of our absolute value function. Notice this time we have the square root function, and our multiple is actually under the operation. So with all of these, anytime it's under the operation, it's going to affect horizontally. In other words, it's going to affect x. If it's outside, it's going to affect the y. So it happens vertically. Okay, so keep that in mind. And so I'm going to start with my square root function again. And so what I want you to look at here when we look at this y is the square root of 2x. We'll do that one first. Is how is that 2 under there affecting your output? And I want my output to be sorry, losing my train of thought. I want my output to still be that nice number. You know, you don't have to have a nice number, but I'm not using a calculator, so I'd like to get this 2x in here as a perfect square is what I'm trying to say. So originally when you had 0, that's going to still be, I'm making a table here with this, you know, thinking about the value of this column as being what's under my operation. Okay, so when you put that 0 in, doubling that isn't going to change the fact that you're still going to get the square root of 0 is 0. Okay? But what I want you to notice is when you put the 1 in, this now becomes a 2. And that's no longer a nice perfect square, right? We just get the square root of 2. That's not as nice as it of an output as it was in the original when we had the square root of 1 is 1. So what I want you to think about here is, okay, how could I get a 1 under here? Or in, you know, that's just one question you could ask. Be more general, how can I get a perfect square? Under the radical. And so think of your set of perfect squares. The first perfect square is 1, but when we plug 1 in for x, we don't get a 1 under the radical. Well, what number in place of x will give us a 1? And the answer is a half, right? 2 times a half will give us a 1 under the radical, and then we'll get our nice square root of 1 is 1. And so what will happen here is, if you notice, the 1/2 is the true input, but that's what creates the 1 under the radical. So you've got 1/2, 1, and this original point actually got moved back here. So let's do another one. All right, our set of perfect squares are 0 and 1 and then 4, right? We did 0 and 1, now let's do 4. So I want this number under the radical to be 4. Well, what does x have to be to get 4 under here? Well, 2 times 2 is 4. And now the square root of 4 is our 2. So this is the true point, but this is, you know, me just creating that perfect square under there. I know it's hard to understand. This is the hardest one, I think, to understand. So we've got 2, 2. What I want you to notice here with both of these is the original, here's your perfect square. The input needs to be half of that so that when you double it, you get that perfect square. So you've got the point 2, 2, and what's actually happening is the original is coming back by a factor of a half. If you half the original x, you've got 2, and that's where that point is going to slide to, so that the output is the same as it was originally. Okay, let's do one more. So now you want the next perfect square in the list. You know, we've got 0, 1, 4. Next would be 9. So what does x have to be so that when you double it, you get 9? And the answer is 9/2, or in other words 4.5 if you would prefer to think of it as a decimal. 4.5 times 2 is 9. And so the original 9/3, which is about here, now becomes, of course the square root of 9 is 3, 4.5, 3. So it comes here, and this is the square root of 2x, right? And the original is the square root of x. So notice again, this, you have to look at it this way. This original graph, it's just like the vertical compression. It's getting compressed horizontally instead. This thing is getting pushed towards the y-axis. So all of these points are half as far horizontally, the y's, or excuse me, the x's in other words, are half as far from the y-axis as they were originally. So if you look at that distance, right, it's half of what it used to be. This distance, half of what it used to be, etc. So it compresses horizontally towards the y-axis. I know this is harder to understand. Just the way you're looking at it, it makes it awkward. You know, you're looking at it this way versus this way. And also it does the opposite of what you think, right? The 2 under there, you would think, oh, that's going to make it bigger, so it should, you know, stretch it like it did with the vertical, but it actually has the reverse effect. So under the operation has the reverse effect. It compresses when the number is bigger than 2, and now when it's bigger than 1, I should say. Now when it's smaller than 1, let's look at 1/2 square root of x. So again, start with, I'll do that in pencil. Okay, so now what x is going to create that perfect square, so that 1/2, you know, 1/2 x is a perfect square, and then the square root of that will be a nice integer. So again, the 0 is not going to change. That stays the same. So now, right, it's not going to be a half. You're going to have to get a output of 1 here, you're going to actually have to double the x. X is going to have to be 2. And then the square root of 1 is 1. So you're going to have the point 2, 1 instead of 1, 1. And now we want to get out of 4. So what number here is this times what is going to give me 4? And the answer is 8. And so the x is going to become 8. Half of that is 4, and the square root of 4 is 2. So you've got the point 8, 2. So see, this actually got pulled up here. And so your graph actually gets pulled to the right, away from the y-axis. That's a horizontal stretch. Okay. So the inside, the transformations that affect the inside, here, you know, a multiple or an addition or subtraction of a number, they actually have the reverse effect, right, of what you probably would expect, versus the vertical ones do what you would expect. You know, a bigger number makes it bigger, a smaller number makes it smaller. Okay, so I had a typo here. I noticed it before I started the lecture, so you want to correct that. These are your horizontal stretches and compressions. So this A is under the operation, and we're going to get a horizontal stretch if that's actually going to stretch if A is less than 1, of course bigger than 0. If that's a negative in there, then you get the reflection through the y-axis that we talked about before. So this is again just A is positive in these problems. And then a compression if A is greater than 1. Now actually we don't use the horizontal stretch and compression very often in algebra. And the reason we don't is because, let's see here, the back of this paper and show you an example. Let's say it was, say you have y equals x squared as your original, okay? And let's do the example, graph y equals 2x squared, like this. The reason we don't do it this way very often is because a lot of times with algebra you can just simplify. This is actually 4x squared. So in this form, we've got a vertical stretch. Whoops. You're going to multiply each original y coordinate times 4. In this form, you've got a horizontal compression. And you're going to multiply each x coordinate. I didn't write this down in the definition, but I'll go back and do it. You're going to multiply each x coordinate by a factor of 1/2. So it's actually the reciprocal of a that you're going to multiply by. And so if you compare those two things, right here, actually, with the multiple of 4, it's going to get, that's a pretty big stretch. So I'm going to change this location of the x-axis here. Okay, so here's the original. I'm just going to kind of estimate since I don't have a grid. Right, here's y equals x squared. The 4x squared is going to take all of these and take everything times 4. So 1, 2, 3, 4. That's going to come up here. 4. And then the original 4 is going to go way up to 12. So this is really going to become a skinny parabola. I'm not even going to put the 12 on there. It's too high up. Okay. So here's y equals 4x squared. But notice that is, if you look at it this way, the x's are multiplied by the half. So this would be multiply each original x by 1/2. This would be multiply each original, when I say original I mean the one from x squared, y by 4, right? Y coordinate is what I mean. Same thing here, x coordinate. So notice here this original was 2, 4, right? So the new y coordinate becomes 2, 16. I said 12 before. What? I meant 16. 4 times 4 is 16. That's way off the graph. The new x coordinate, however, is 1. So that is your x coordinate times a half. That's 1, 4. So notice when you plug the 1 in, 2 squared is 4. So you can think about it in two ways. It's a vertical stretch, but it's also a horizontal compression. Most of the time with algebra, we can just do it with the vertical stretch. We don't need to use the horizontal compression or stretch, you know, whichever one it is. But if you take trigonometry, you're going to use these ones a lot more. These are used in the trig functions a lot. And of course, you might just have a problem like this, and you don't know the formula, and you still need to be able to do it in terms of a horizontal stretch or compression. So you still need to know it. It's just not as common, okay? So I said for this one, you're going to multiply each x coordinate by a factor of 1 over a. So that way if a is bigger than 1, you're actually getting a smaller result, right? And then if a is a fraction between 0 and 1, its reciprocal would be a larger number than 1. Okay, well let's put this all together. These last examples use possibly any or all of these. All right, the first one, we have our y equals x squared as our basic shape that we would start with. And now, again, start from inside and work your way out. This is going to move it right 4. All right, let me write this over here. So this is right 4. And there's actually 4 of these transformations here being used. The negative is separate from the 2. So this is going to be a stretch of 2 vertically. This is going to be a reflection through x-axis. And then this last one will be up 3. Okay, so you don't have to do that all at once. You can put extra graphs in here if you need to. Just like on the test, you would mark which one is your final answer, right? And just make sure you label your final answer. Once you get better at it, you can kind of keep track and maybe do it all at once. Okay, so now we go over 4. So here, and I'll put several steps in here. So this one, and you know the graph of each, or the equation of each step, I should say. That's going to be x minus 4 squared. Just put it in there lightly. The 2 is going to stretch it. So you're going to take all the original y's and multiply by 2. So 4 is going to go to 8. 4, 8. So here is the next one. Again, just put it in there lightly. That's y equals 2 times x minus 4 squared. Hopefully you can see it. Okay, maybe I'll make it a little darker. Here's the original. All right, here's second step, right? So here's 1, here's 2, here's 3. Next we're going to reflect. So this skinnier parabola gets reflected. So, instead of, I put that at 3 instead of 2. I'm sorry. Let me just slow down a little. 2, 2. That's why my shape doesn't look quite right. So it's still the parabola, it's stretched though, right? So the original basic shape isn't completely preserved. It's still a parabola, but it's now a narrower parabola. Okay, so 2 goes down to -2, and then the 8s go down to -8. So this one is our -2 times x minus 4 squared plus 3. So that's our step 4, if we count the original as the first step. And now the plus 3 moves this whole thing up 3. So I'll make this one blue. 2, 2. So this is where it's helpful to memorize that, out 1, down 2 we went, out 2, down 8. So if I do those same things, I'll get the right shape. 2, 4, 6, 8. Or you could just move this up 3. All right, so the blue one is my final graph. Step 5. Okay, so now our new vertex, and this is a little bit of review from, like, if you took intermediate algebra, remember finding the vertex, the HK, 4, 3, that's the vertex, 4, 3, and then remember this, looking at this to see if it opens up or down. That all comes from the transformations. All right, let's look at the next one. So we have our absolute value function. We'll start with that. Part of this is being able to recognize what the base operation is. It's absolute value. Y is absolute value of x. Okay, so this one we have inside a shift of, addition of 5, so that's going to shift 5 to the left. The 1/3 out on the outside is going to compress it towards the x-axis, and then the -7 will shift it down. So I'll show each step again. So we'll call that number 1. Move it over to the right 5, and the v is nice and easy to graph. So that is absolute x plus 5. Now we take each of those originals times a third. A third isn't the nicest fraction to work with. You know, so you have 1 and then and then 2 times a third is 2/3. So that's going to be here. 3 times a third is 1. And that's plenty. That's a nice accurate graph. And of course we know these are two pieces of line, so they just keep going straight out. So we've got y is 1/3 absolute x plus 5. So this was step 2, this is step 3. There's no reflection on this one. We just need to shift this down 7 now. So from here, 1, 2, 3, 4, 5, 6, 7, the 1/3, you know, just use that as your baseline, and then you can use the, you know, just go up from there. 1/3, 2/3, and then we went up 1. Whoops. Okay, so there is our last final answer, our last graph, step 4. Okay, one more. This one's a little different because the way things are ordered. It maybe is a little harder to interpret all the transformations. We've got the 3 minus 2 times x plus 1 cubed. Okay, well, we're going to start with the basic function, which is the cubing function. So I'll graph that quickly here. Should hopefully be starting to memorize those. So when I do that, you're not surprised. So remember, with this one, it's over 1, up 1, down 1, over 2, up 8, down 8. Okay, the way this is written, well, you should be able to see that there's a shift of 1 to the left. You should be able to see there's a stretch of 2. And then there's a minus here. And then this gets a little tricky. But really, this here is a plus 3. Okay, so this is going to move it up 3. It might help you to rewrite it like this. Whoops, that should be a 2. So now maybe it's easier to see. This is a, you know, up 3 shift, and this is a reflection, the negative. So we're going to move left 1. So here's our new y equals x plus 1 cubed. Now we're going to reflect it, stretch it by a factor of 2, and then reflect it. I might do that in one. These are so close, it's going to get really messy, so I'm going to do that in one step. So when you do your stretch, this is going to stay the same. You go over 1, up 1, right? You're going to double that and make it 2, but then we're going to reflect it right away. And then this one, when you stretch it by 2, reflect, it's going to come up here. And then the 8, when you double that, it's going to go way up to 16, so that's way off the graph. And then it's going to reflect down here, of course. 16 is going to be way down, so I'm not going to include that. You know, keep in mind though that's going to create this really elongated shape. So it still has that S kind of curve, but it's very stretched out. In fact, this is probably not stretched out enough on this end. This is going to go all the way down to negative 16. And this up like that. Okay, so that would be negative 2 times x plus 1 cubed. And now our final step is to add the 3. So this one will get moved up 3, up 3, up 3. Again, the next set of points is too far off the page, so just do your best making it look you know, stretched out. The blue one is our final answer. Okay, one more example. In this example, actually they did problems like this in our textbook in the last section, but I'd like to wait until after we talk about transformations because it helps with the graphing instead of having to plot so many ordered pairs. So with the piecewise function, remember you have more than one formula, but the formula only applies to certain parts of the domain. So if we know our basic shapes, we know this part is a parabola, and then we can use our transformations to help us graph it, but we need to use, make sure that parabola that we graph is restricted so that we only take the part where x is less than 1. And then this one, we know this is our square root function. It's going to have this shape, half a parabola, right, on its side. And that is, again, we're only going to take the part where x is greater than or equal to 1. We have to make sure we pay attention to the restriction. We wouldn't want to double up the two graphs, the two pieces, because then we wouldn't have a function. So the cutoff here is going to be at 1. So this half is going to be this piece to the left of, or to the right of 1, I'm sorry, is going to be this piece. Okay, but let's just ignore the pieces for now and just think about what this shape would be. We'd have a parabola, that's our squaring function, shifted 1 unit to the left, then it's reflected, and then up 1. There's no stretch, so if we can remember that basic shape, it'll help us. So we're going to shift it 1 to the left, and then, originally it would look like this, but we're going to reflect it, so it's going to look like this, and then move it up 1. I don't want to put all these pieces in here, it'll get too messy, but we move it up 1. So the vertex is here. If you can remember the vertex, keep track of that, and then it opens down. There's no stretch, so go out 1 in each direction, down 1. And then out 2 in each direction, down 4, because 2 squared is 4, right? And so we would have this shape like this. And I'm doing it very lightly because I need to pay attention now to my restriction. This is only if x is less than 1. So where is x1? If you did plug 1 in here, 1, and I don't want, this isn't actually the function value, so I'm just not going to write f at 1, because f at 1 you'd have to use this formula, okay? But if you did plug 1 in, 1 minus 1 plus 1 squared would be 1 minus 2 squared is 4, which is negative 3. See, that's right here, but because of the restriction, we would put an open circle there. And so this part is the part of the graph we want. The open circle shows that graph goes up to that point but doesn't include that point. Okay, so that's our first piece. Excuse me. Our second piece, we have our square root function. So again, if you think about where that would start, now you're going to move it 1 to the right, and then this is going to be down 3. So actually this start point 0, 0 actually moves and lines up with the end of the first piece. Notice if you plug in, so the f at 1, now I can use this notation because this is 1, square root of 1 minus 1 minus 3, that's the square root of 0, which is 0, and so we just get negative 3. Because the starting point of this matches up with the end of the first piece, now we're going to shade that in. That's actually the true function value. And now we know it's the square root, so we can go, over 1, up 1, over 4, up 2. We know the basic shape. Okay, so this ended up being like this. Now, one piece doesn't always line up with the next piece. So you could have say that this was a plus 2 instead of a minus 3. This part right here, you'd still shift over 1, but then you'd move up 2 like this, right? And that would be your square root up here. Then this would have the closed circle, and this would be, of course this wouldn't be here, This would be open because you can't have both of these points on the graph and still have a function. So there can be a jump between the two pieces. These ones just happen to line up, and we got a nice continuous curve then instead of a jump. But keep in mind, it doesn't always line up. And then if you're not sure if your graph is right, just test a few function values. Notice that when you plug in like -2 here, of course you have to use this piece for that. -2 plus 1 is -1. -1 squared is 1. 1 minus 1 is 0. That agrees with what I have here on my graph. And you can test some other points as well. But if you understand those transformations, it'll help you a lot. You don't have to plot so many ordered pairs. You know the basic shape. Okay, that is it for this section. Let me know if you have any questions.